Wow, welcome to Mathematics and Science Meal, a beautiful program designed to help students in the study of mathematics and sciences. Remember that in Mathematics and Science Meal, we look at mathematics and all the sciences. There is need for you to subscribe to our YouTube channel, Mathematics Meal 1, and then you follow us on Facebook, Mathematics and Science Meal. Alright, today we are going to look at physics meal, and the topic we are going to consider is wave, part 1 of wave. Remember, wave is a very broad topic. It's a broad topic in physics, so we have decided to break it down into different parts so that it will be easy for students to understand it. Remember that you need to like this video, whether you are watching it through YouTube or through Facebook. Like our video and also leave a comment for us. Thank you. Today, what are the objectives that we are going to look at? By the end of the lesson, the students will know the following: 1, meaning of wave, and what types of wave. So let's begin. What do we mean by wave? So look at the first objective, meaning of wave. Alright, the word wave is not a new word. It's not a new word to you, because I know from time to time someone may ask you to wave your hand and you just do like this. In the church, most times the praise leaders, they will always say, rise up and wave your hand unto the Lord, and you begin to wave your hand. And you notice that the moment you are waving your hand, you're actually disturbing your hand. That's true. You see, as I'm disturbing my hand is moving to and fro. It's oscillating. There is a disturbance that is causing the hand to oscillate. So wave is associated with disturbances. So we are going to define wave as a disturbance. So wave is a disturbance that travels through a space or mass, transferring energy from one point to another. So the disturbance that travels through a space or mass, transferring energy from one point to another, that's what? That's wave. That's wave. So this disturbance can be in the form of oscillations or vibrations. So we can also say that a wave is a vibration or an oscillation that travels through a space, transmitting energy from one point to what? To another. Now, from this definition, it is important to point out that wave transmits energy but not mass. Wave will not transfer matter from one point to another. The only thing that is being transmitted by wave is what? Energy. Energy is transmitted from one point to what? To another. But there is no movement of matter from one point to another. What we are trying to say here is that the medium through which the wave will pass will not move. The medium will remain the same. For example, if I have this, let's say this is a string or a rope, and I tie this rope on a pole and swing it, you know, it's going to rise and fall, rise and fall, rise and fall, rise and fall in that order. It doesn't mean that this particle, the particles of the rope are moving. No, it's only transmitting energy, because this part of the wave will still, of the rope will still remain here, or this part of the string will still remain here. This part of the string, this part will not move and go to this point, no, but it's just transmitting energy. So energy moves in the medium, but not the medium. The medium is not moving, because how you will know that? If you give a mark, let's say we have a mark here, a mark somewhere here, even if we swing this mark will not go to that point. It's not possible. It will still be in this position, because when this rope comes to its resting stage, you will discover that this mark on the rope will still remain here. So matter is not transmitted during wave. What we transmit during wave is what? Is energy. Energy is what we transmit during wave. So energy is transmitted during wave. Now wave can travel through a space, that's a vacuum. In other words, such a wave will not require a medium through which it will travel, or a wave can be transmitted through a mass. So there are waves that require material medium, while we have some waves that will travel through a vacuum. So waves can be mechanical or electromagnetic. Waves that require material medium are called what? Mechanical waves. So mechanical waves are waves that requires material medium, while electromagnetic wave do not require material medium. So mechanical waves require material medium. So mechanical waves need a medium through which they will pass, or through which they will be propagated. So, but electromagnetic wave, they don't need any material medium in order to transfer their energy. So mechanical waves, examples of mechanical waves, examples of mechanical waves are sound and water wave. Sound and water waves. Sound and water waves are typical examples of mechanical wave. Then examples of electromagnetic waves. Electromagnetic waves are the light wave and radio waves. Now you know, since wave transmits energy, means that the various forms of energy we have can also be transmitted through wave. Like when we talk about sound wave, it transmits the sound energy. Light wave, it transmits the what? The light energy. So the wave that we help us to hear, that's the sound energy. Then the rays, or the wave that will help us to see, that's what we call the what? The light energy. And that is transmitted by light what? Light wave. Alright, let's move on. So with this definition, I believe that we have been able to explain what a wave is. We said a wave is a disturbance that travels through a space or mass, transferring energy from one point to another. So the only thing that is being transferred during wave motion is energy. So matter will not be transmitted. The medium will not move in the course of wave motion. Only energy is transmitted from one point to another, but the medium will not move. Now this disturbance we are talking about can occur in form of oscillation. You know your pendulum, like as I'm waving my hand now, there's to and fro. Then it can also occur as a result of vibration. When you have a string, you swing a rope, it moves up and down. So it's another form of disturbance. So this disturbance can be in form of vibrations, or it can be in form of what? Oscillations. Then we have said that wave can be mechanical. A mechanical wave we require what? A material medium for its propagation, for its transmission. It has to move through a material medium. But electromagnetic wave will not require what? A material medium. And we have given examples of mechanical waves. We say that sound and water waves are mechanical waves, while light wave and radio waves are what? Electromagnetic waves. So we need to continue on the second objective. So we need to look at the types of wave, types of wave. There are two main types of wave. Main types of wave. If we name them, we have the transverse wave and we have the longitudinal wave. So we have two types of wave, transverse wave and what? Longitudinal wave. So we're going to take time to describe these two types of wave and some of the terms that are associated with them. So the first one is transverse wave. Transverse wave. What do we mean by transverse wave? The transverse wave. Now, if we have a wave that its direction is perpendicular to its vibration, that wave is what? A transverse wave. So a transverse wave is a wave that travels in a direction that is perpendicular to its vibrations. So a transverse wave is a wave that travels in a direction that is perpendicular to its what? Its vibration. Let's say we have a string or a rope like this. Now you look at this rope, you did not swing it. So this rope is at a resting position, what we may refer to as the equilibrium point. Equilibrium point. So there is no wave yet here. So at the resting stage, that's the equilibrium point. But when you swing this, let's say, let me draw this to this point. Let's say I have this here. And I'm holding this rope here and I swing it. Definitely we'll have a motion like this. Something like this. We have a motion like this. Now you will notice that the wave is moving in this direction, right? But the vibration is up and what? Down. So you see that at each time the vibration moves up and moves down. So you discover that the vibration is up and down, the direction is like this. So two of them will form a right angle. So the vibration is at right angle to the direction of the wave. So when the vibration is perpendicular to the wave, to the direction of the wave, such wave is known as what? A transverse what? A transverse wave. So in a transverse wave, the direction of the wave is perpendicular, that is at right angle, that is forms angle 90 degrees with the what? Vibration of the what? Of the wave. So the vibration, the up and down movement is perpendicular to the direction. So the wave is moving like this in that direction, while the vibration is moving up and down. So they will meet at angle what? 90 degrees. So when the vibration is perpendicular to the what? To the direction of the wave is said to be what? A transverse what? Wave. And typical examples of transverse wave: water wave and light wave. So examples, what are the examples? What are the examples of transverse wave? Water and light waves are examples of transverse wave. Now there are terms that are associated with transverse wave. We're just going to use a diagram to show those terms. Now the resting point in a transverse wave is the equilibrium point. No vibration here, no oscillation yet. So this line shows the resting stage or the equilibrium stage when there is no vibration. At this point, the displacement is what? Zero. At this point, the displacement is zero. So this is the equilibrium point. The equilibrium point. The equilibrium point is the equilibrium position is the resting position of what? Of a transverse wave. So we have the first term that we need to look at, the equilibrium position. So we talk about under transverse wave, we have what we call the equilibrium position. That's the equilibrium position. So this is the resting stage or the resting point of the particles in a wave. So this is the resting point. That's the equilibrium point. Now if you now begin, there is a wave motion now, rise and fall, rise and fall, rise again, and we have this. We have the highest point, we have the lowest point. The highest point on a transverse wave is what we call the crest. So we have crest. This is the highest point on the transverse wave. While the lowest point is called trough. This is the lowest point on a transverse wave. So we have here, this is the crest. That's the crest again, that's the crest. This is the trough. That's the trough. Don't have another one here. So this trough and trough, crest, crest, crest. Now it is important to note that the distance from the equilibrium point to the trough or to the crest will be the same as the distance from the equilibrium point to the what? To the trough. So from the equilibrium point to the crest will be the same from the equilibrium point to the what? To the trough. The equilibrium point from the equilibrium point to the crest is the same as from the equilibrium point to the what? To the trough. So equal distance. So from the equilibrium point to the crest is the same as from the equilibrium point to the trough. So the distance, you have to note that the distance from the equilibrium position to the crest is the same as the distance from the equilibrium position to the trough. Now we are still going to revisit crest and trough in relation to other terms associated with wave, like the wavelength. We're going to use the term crest and trough to describe wavelength of a wave. We are going to look at that when we now consider second part 2 of wave, where we're going to look at the basic terms associated with wave, where we'll see amplitude and the rest of them, wavelength, frequency, period. Then we look at speed of a wave, and then we generate some expressions that we are going to use for calculations. So that will be in part 2 of wave, where we will look at basic terms associated with wave. All right. So these 3 points or 3 terms are very, very important when we are looking at transverse wave: the crest, the trough, and also the equilibrium position. Then number 2, the second type of wave is what we call the word longitudinal wave. Longitudinal wave. A longitudinal wave is a wave that travels in the same direction as its vibration. So in longitudinal wave, it travels in the same direction as the word vibration. In other words, the vibration and the direction of the wave are parallel to each other. They travel in the same direction. Sound wave is a typical example. Sound wave is a typical example of longitudinal wave. So the sound, the direction of sound wave and the vibration, they are the same. The vibration and the direction of the wave, they are the same in sound wave. So that's what makes it a typical example of what? Of a longitudinal wave. Now in transverse wave, we have 2 important regions. That's the point we call the what? The crest. And we have the point we call the what? The trough. Then in longitudinal wave, we have 2 points of interest. The point we call the compression region, and the point we call the region we call compression region, because it's not necessarily a point. And then the region we call the what? Rarefaction. Rarefaction. It's not refraction, but rarefaction. So we have in longitudinal wave we have compression and rarefaction. Compression. What do we mean by this compression and rarefaction in longitudinal wave? What do we mean by that? Compression and rarefaction. So compression, this is the region where the particles are closest to one another. So when the particles are closest to one another in a longitudinal wave, that region is known as the what? The compression region. Then on the other hand, the rarefaction, this is the region where the particles are further apart from one another. So when the particles are further apart from one another, that is the rarefaction. So we can have this. Let's use a simple diagram. We have this. See this? Then the particles now spread, and you have this again, and the particles now spread. So this region where the particles are very close to one another, we call it the compression. Why this one is the what? The rarefaction. This compression, rarefaction. So when the particles are further apart, then we have the rarefaction. But when the particles are closest to one another, we refer to them as what? The region of compression. Alright, so far so good. I believe that you have enjoyed the class. Remember, we started with the meaning of wave. We said that wave is a disturbance. When you wave your hand in the church, they say wave unto the Lord. You do that. Some of you may use two hands, and you see you are disturbing your hand when you do that. To and fro, that's oscillation. You can still move your hand up and down like this, still to and fro like this. You can still move your hand up and down, that's vibration. So once you cause a disturbance, and that disturbance transmits energy from one point to another, that is wave. That is wave. Remember, we say that wave will not transmit matter, but rather wave will transmit what? Energy. It doesn't transport matter, but it transmits what? Energy from one point to another. We say that wave can be mechanical or can be electromagnetic. We explain that based on medium. We say that mechanical wave will require a material medium, while the electromagnetic wave will not require what? A material medium. Then we looked at types of waves. That's the transverse wave and the what? And the longitudinal wave. They are the two types of waves that we have considered, and the terms that are associated with those terms, types of wave, crest and trough, and equilibrium position or equilibrium line as it concerns the transverse wave. And then in longitudinal wave, we considered the compression region and the rarefaction region. That's where we are going to end our class today. I believe you enjoyed this class. We are going to come back next time to look at the second part of wave, where we'll be considering the basic terms that are associated with wave. Keep watching our videos and keep sharing our videos. Remember, there is need for you to subscribe to our YouTube channel if you have not done that, and also follow us on Facebook. I love you all. God bless you.